Today in the workshop, we're working with the Raspberry Pi Pico microcontroller. We'll hook up a collection of I/O devices to the Pico, and we'll make them work using MicroPython. We've ordered the Pico with everything on it, so welcome to the workshop. Well, hello and welcome to the workshop where we are welcoming a brand new microcontroller. Now, I'm sure you've probably heard that near the end of January, the folks at the Raspberry Pi Foundation announced a new product, and for the first time it was not a microcomputer, it was a microcontroller, the Raspberry Pi Pico. Now, the Pico is built around their own silicon, the RP2040 chip, so it's a brand new experience for all of us. And in the last couple of weeks, people have been scrambling to get their hands on some Picos, to get their hands on Pico accessories, and to learn a little bit more about this little microcontroller, which goes for all of $4 US. Well, I've been no different. I've managed to get my hands on a couple of Picos. I've got Pico accessories on order. I got a few that just arrived here yesterday afternoon, and so we'll be doing a lot of work with the Pico. But what I wanted to do to start off was just see how you could use this thing. So what I did is I put this solidless breadboard together, and I built what I guess you could just call a thing. And what this thing is a Raspberry Pi Pico attached to a number of different I/O devices. And we're going to hook all of these things up, and then we're going to go through it section by section so you can see how you can use MicroPython to code for these devices. And armed with that knowledge, you should be able to hook up just about anything to a Raspberry Pi Pico. So before we get into the specifics of the Pico, let's take a closer look at this little everything breadboard I have here. And so here's my breadboard with the Pi Pico and a number of different components interfaced to it. You can see the Pi Pico buried underneath all of these jumper wires here. And just back in the corner here, you can also see the edge of the Raspberry Pi 4 that I'm using to control everything today. Now, to give you a tour of what's on this breadboard, there is an LED over here. It's actually an RGB LED. It's a bit difficult to see because of its transparent nature. You can see the three dropping resistors for it. You've got a potentiometer over here. Of course, that's going to be used to test the analog inputs. A couple of push button switches, a couple of momentary contact ones, a red one and a black one. This is an OLED display. It's an I2C device as well, so we can see both how we can work with displays and how we work with I2C. And I've got a DC motor over here, and I've got an H-bridge controller to drive the DC motor, and I'm just using one side of the H-bridge because it's actually capable of controlling two motors. It's just a little 6-volt DC motor, so I've got 6-volt power supply for it over here. And now let's go and learn a bit more about the little Pico that's going to control all of these devices. The Raspberry Pi Pico was introduced by the Raspberry Pi Foundation in January of 2021. This is the first microcontroller in the Raspberry Pi family. The Pico is powered by the RP2040 microcontroller chip. It has multiple PWM-capable GPIO ports, I2C buses, SPI buses, analog-to-digital converters, and UARTs. The Raspberry Pi Pico retails for only $4 US. The Raspberry Pi designed RP2040 chip has also been licensed to other manufacturers, and so you'll start seeing other boards built around this chip very soon. The most predominant feature on the Raspberry Pi Pico board is the micro USB connector. This is for both data communications, and it will power your Pico. The onboard LED is connected to its own exclusive GPIO port. It is the only LED on the Pico, which gives no indication whatsoever of when power is applied to it. The boot select button allows you to select which bootloader to use when you're starting the Pico up. The Pico supports 2-wire serial debug through a debug connector at the bottom of the board. In the center of the board, you'll see the Raspberry Pi designed RP2040 microcontroller chip. The RP2040 is a 32-bit dual-core ARM Cortex-M0 Plus chip. It runs at a normal clock speed of 48 MHz and can be boosted to 133 MHz. In the Pico implementation, there are 2 MB of onboard external flash memory as well. There is also an onboard real-time clock and an onboard temperature sensor. The Pico has been designed to either use pins or to be surface mount capable. The design has 8 ground points plus an additional one as part of the debug. You'll notice that the ground points are evenly spaced on the Pico board. They can also be distinguished in the fact that all the ground connections have square pads instead of rounded ones. V-bus is an output of the micro USB cable voltage, which will usually be 5 volts. If there's no micro USB attached, there is no output from V-bus. VSys is the power input for the system. You can run the system on anything from 2 to 5 volts, although the Pi Pico is a 3.3 volt logic machine. The 3V3 output on pin 36 is a 3.3 output from the Pico's internal voltage regulator. You can use this to power external devices, but don't exceed 300 milliamps. The 3.3 volt enables the 3.3 volt power supply on the Pico board. It can be used to externally turn the Pico on or off. The run connection is an enable connection for the RP2040 microcontroller. It can also be used as a reset for the microcontroller. There are 26 exposed GPIO pins on the Raspberry Pi Pico. There is also a 27th GPIO pin that is internal and is used for the onboard LED. The Raspberry Pi Pico has 12-bit analog to digital converters. There are 3 ADCs available plus an internal analog to digital converter. The internal ADC is used for the temperature sensor. The ADC ref and the ADC GND connections can be used for an external voltage reference to improve the accuracy of the A to D converter. The Raspberry Pi Pico has 2 I2C buses with a number of connection options. It also has 2 SPI buses, also with multiple connection options, and 2 UARTs as well. It supports 16 PWM channels in total, again with a number of different connection options. Now, the Raspberry Pi Pico can operate as a normal microcontroller. It can be powered using the micro USB port. It can also be battery powered, as it is capable of operating at voltages as low as 2 volts. The Raspberry Pi Pico can also operate as a USB device. When plugged into a computer's USB port, the Raspberry Pi Pico can operate as a USB device. This can be useful for building things like keyboard emulators. The Raspberry Pi Pico can be programmed with MicroPython or with C++. We'll be using MicroPython in today's experiments. So now let's take a closer look at the Raspberry Pi Pico. Now here we have a Raspberry Pi Pico, actually 2 Raspberry Pi Picos, in the midst of a number of other microcontrollers and a few microcomputers. Now here is a Pi Pico with all of its feet soldered onto it, ready for plugging into a solderless breadboard. And at the back over here you can also see there's a 3-pin connector, and that's an optional debug connector. We won't be working with that today, but in the future we'll take a look and see what that's all about. Now this is how you get the Pi Pico. When you order one, it doesn't have any feet on it. You need to solder that on, and we're going to do that in a moment. But before we do, let's compare the size of our Pi Pico to a few other very common boards. Now, keeping it in the family, going to a microcomputer, we've got the Raspberry Pi Zero, and so you can see the Pi Pico is reasonably smaller than the Pi Zero. It has the same number of I/O ports, but of course the Pi Zero also has a micro SD card reader, an HDMI port, 2 micro USB ports, and one of them for power, and a camera connector at the back, so it beats the Pico with a lot of capabilities. Interestingly, these are $1 apart in price, the Pico being a $4 US board and the Pi Zero being a $5 one. Now over here we've got the head of the Pi family, the Raspberry Pi 4, and as you can see, you could fit quite a few Picos onto a Pi 4, so perhaps you can make an expansion hat for the Pi 4 that has multiple Picos on it and pretty well control anything. Now I've got a few other boards here that aren't Raspberry Pis. Now this is an Arduino Pro Mini, and as you can see, it's a bit smaller than the Pico. It has less I/O pins. The Pro Mini is essentially the same as the Arduino Uno in terms of capability. It's an 8-bit AVR, so it's no match for the Pico in terms of capabilities or the number of I/O pins. And over here we've got an Arduino Nano 33 IoT, and this is a very interesting board. It's using a SAMD21 processor, so it's a very fast board, so it's probably capable of similar power to what we're going to get in the Pico. It also has built-in Wi-Fi and Bluetooth. It's got an extra module on the board, and the Pico has no connectivity like that. Now, one board that you'll probably want to compare the Pico to quite extensively would be this, and this is of course the Cduino Xiao, and as you can see, the Xiao is a lot smaller than the Pico. It's about, you probably get 2.5 if you put them sideways, maybe even 3 Xiaos in the space of a Pico. Power-wise, these are likely to be similar. It would be nice to put these two boards against each other one day, but in terms of the number of I/O ports, of course, the Pico has you built. And cost-wise, the Xiao is a $5 US board, and the Pico is a $4 US board, so that's really cutting it pretty close. You're getting an incredible amount of power these days in very tiny packages. And so now let's go and take a look and see what we need to do to take this Pico and make it look more like this Pico. Now here are the parts and equipment that we're going to need to solder the pins onto the Pico, and of course the first piece of equipment we're going to need is the Pico itself, and they come in these packages over here. I guess they just come off the Pico machine like this, and so I've taken one out. We can move these over here. Now you're going to need some pins for it, and these are 40-pin male header strips, and they're very commonly available, and by a great coincidence the Pico happens to have 20 pins, and so we can cut one of these in half and use this as the pins for it. I've got 3 other pins over here. Now this is optional, but there is a debug connector at the very end of the Pico board, and if you want to put a connector on that, you're going to need a few extra pins for that. I've also got a little pair of diagonal cutters, and that's just to cut this 40-pin strip into 2 20-pin strips. Now, of course, over here I have a soldering iron, which is not plugged in at the moment, but I've got a very thin tip on the iron, and that's important because you want to be able to get in at those individual pins. And of course, you're going to need a stand for the iron. You're going to need a soldering sponge over here, and of course some solder over here. Now, there's a couple of other things I've got here which you may not have expected. First of all, this little stack of post-it notes is this being used as a spacer when I solder this piece in. I'll show you what I mean in just a moment here. And this is what I use to hold the pins together. Now there's a couple of ways you can do this. Some people like to put everything onto a solderless breadboard and then solder it into there. I'm not crazy about that idea for a couple of reasons. First of all, I'd be a little concerned about the heat going down into the pins and melting any of the plastic in the breadboard, although if you're quick about it like you should be, that isn't going to happen. There's also a possibility of a solder splatter getting somewhere into your breadboard. So you can use builder's putty as well. That's another way to hold them down. But I like doing it like this, and let me show you with the 3 pins over here what I mean. I'm going to put these pins in, and now they're held in the board like that. And this is where my little post-it note comes in over here, actually, because unfortunately I can't use these pins to support the rest, because although everything is on a 0.1 of an inch grid this way and this way, it isn't this way. These holes don't match up with here, so they don't line up that way. But if I turn this upside down and put it on top of the pins, I'm all ready to solder these 3 pins, the debug pins, onto my Pico. So let's just solder these 3 pins at the top here. These are the debug pins, and the connector's going the opposite direction of the GPIO pins. And there we go, it's as simple as that. And now we've got a connector on here for the debug, and we can get on to soldering these GPIO pins. Now I've cut my male header strip into 2 pieces, 220 pin pieces, and I've put it down into this perf board. And I actually find that cheap perf board, the type that doesn't have the plated through holes, works better for this. If you use 2 layers of it, it really holds the pins quite tightly, and it lets you get them soldered at a good angle so that it'll fit into a breadboard later. So let's just put the Pico down onto its pins. There we go. And we shall begin to solder this. Okay, we'll flip it around. Okay, now we can take the Pico out of the board, and as you can see, we've got our header on and it looks pretty nice. I'm going to go and clean up these connections a little bit, and then we'll be finished soldering up our Pico. Now you don't have to clean the flux and the resin off of the board, it'll work just fine without doing that, but if you want to make it look nice and shiny, you're going to need a couple of chemicals to do it. And the most important one is some flux remover, and you can get this at your local electronics store. In fact, they probably have a better price there than you'll find it online, because shipping this stuff can be expensive. And this is something you can find just at your drugstore, and this is isopropyl alcohol. Now this is not rubbing alcohol that has the methanol in it. This is just basically isopropyl and water, and you're going to use that just to clean off the residue from this. I've also got some essential safety pieces of equipment you need, of course. You're going to need some goggles to keep from getting this stuff in your eyes. You will need a mask because you don't really want to breathe this stuff, and naturally you will need some gloves, and I think most of us have this safety equipment around the house these days. And also for doing the work, an old toothbrush comes in very handy, and just an old plastic container that you can dump the stuff into and work from there so that you don't pollute your supply. Now when you're working on this, work in a place like a basin or something where it is safe. Make certain you are wearing appropriate clothing. Don't wear your best clothes by any means. I basically just used the flux remover first, and I used a toothbrush to scrub all of the little pins. And then after that, I clean everything off with the isopropyl alcohol. And then you can just let it dry. If you have an air dryer, you can use that as well. Do not use a heat gun on it, but a hair dryer at low setting would also work. Or you can just let it sit and dry, and then you should have a nice and shiny Pico. So now our Pico is back from its bath, and it's looking all clean and shiny. There doesn't appear to be any resin or flux around any of the pins. And we can flip it over and we can see the same for the debug pins over here. Now, cleaning it and taking the flux off of it is an optional step, of course. You don't have to do that. The flux and resin is not going to harm anything, and your Pico will work perfectly fine. So if you don't have the chemicals or the facilities to do it safely somewhere, please don't worry about it. But I like to do it, especially as in this case our Pico is about to be introduced to a bunch of different input and output sensors, and we do want it looking its best. Now let's go and see what we can do with this clean little Pico. Okay, now that we've got our Pico all soldered up, it's time to go and do something with it. And for this, we're going to need a computer and we're going to need an IDE. Now, the IDE I'm going to be using today is the Thonny IDE. Now, this is the IDE that Raspberry Pi has recommended, and although it's not the most powerful IDE, it is certainly going to be capable of doing what we need to do with it today. I'm also going to use the Thonny IDE on a Raspberry Pi, on a Raspberry Pi 4, using the latest version of the Raspberry Pi operating system. You can also get the Thonny IDE for Windows, Mac, and Linux, so you can use any computer you'd like when you're working with your Pico. So let's go and see how we do that. Okay, now that we have our Pico all soldered up, the next step is to put MicroPython onto it. What I've done to it right now is I've taken a micro USB cable, I've connected the micro USB end into the Pico, but the other end is currently not connected to anything. In the meantime, I've got my Raspberry Pi 4 all booted up with a fresh copy of the Raspberry Pi desktop, and I'm getting ready to plug the cable into the USB port on the Pi. Now, as I do that, though, there is a button here that says Boot Cell on it. I want to hold that down while I plug the cable in, and hold it down for a couple of seconds and then release it. And I get this removable medium is inserted menu, and it's asking me if I want to open this in the file manager, and I do. And this is our Pico. It has in this mode come up as actual removable media off of our file menu, and the same thing would happen, by the way, under Windows or Linux or Mac. You would get this as coming up just as if you had plugged in, let's say, a USB drive or something. Now there's an index.html file here. Let's click on that, and that of course will open a web browser, and it redirects us to the Raspberry Pi Pico page. We'll say OK to the cookies warning up over here and go down to where it says Getting Started with MicroPython. We'll click that and we'll look at this menu over here, and it says we can download a file. And so let's go and download this file, this UF2 file. And so we're going to do a download, and the file has already downloaded. It's a very small file, and we'll do show in folder over here, and that'll open up a second folder. We can close the web browser now. And this file over here is the latest greatest version of MicroPython, and all we need to do is drag that file into this Pico directory here. And once we do, the Pico will reset itself, and you'll notice that the file menu for it went away and it no longer appears as a file. Now we're going to be using the Thonny IDE, which comes installed on the Raspberry Pi. So you can just go into Programming and you'll see the Thonny Python IDE. We'll click that to open it. And at the bottom here where it says Python 373, we'll click in there, and we will see the Raspberry Pi Pico MicroPython, and we'll set it up there. And in the bottom over here, which is what is our shell, we'll see that it came back and it said MicroPython version 1.14 on the Raspberry Pi Pico. Now this at the bottom is our shell, and up here at the top is our editor, and we can go directly into the shell if we want and work on things over here. And let's do and it came back and printed hello world. And so we can work directly in the shell, or we can work up here on the editor, and I'll do basically the same thing here. And then we can run that. And first we want to know where we need to save it to. Let's save it to our Pico, and we'll give it a name, test.py, why not? And it runs, and it says hello world. And so we can run programs from the editor and save them either onto the computer or onto the Pico, or we can run directly down here in the shell at the Pico itself. And so we're now ready to begin all of our experiments. So now it's time to begin our breadboard experiments, and we're going to begin with some of the most elementary I/O devices there are. We're going to be using our RGB LED and our 2 push-button switches. LEDs and switches are simple electronic devices that are very useful for illustrating basic digital I/O concepts. The Raspberry Pi Pico has 26 GPIO pins, and most of them support pulse width modulation. You should remember that the Pico is a 3.3 volt logic device when you're interfacing other things to it. The Pico has internal pull-up and pull-down resistors, which are useful for minimizing the amount of circuitry you need. In our experiments, I'm going to be using 3 LEDs, a red, green, and a blue one. However, I'm going to have all 3 of them in the same package. This is a basic RGB LED. You can use this, or you can use 3 discrete LEDs if you wish. In addition to the RGB LED, you're going to need a couple of push-button switches. These are momentary contact, normally open switches. I used a red one and a black one. You'll also need 3 dropping resistors for your RGB LED or discrete LEDs, and I used 330 ohm resistors for this. We'll begin by connecting pin 14 of the Pico, which is GPIO pin 10, to one of the resistors, and then to the anode of a red LED segment. We'll connect pin 15, which is GPIO 11, through a resistor to the green segment. And we'll connect pin 19, which is GPIO pin 14, through a resistor to the blue LED segment. We'll connect one of the Pico's many grounds on pin 23 to the common cathode connection on the LED. Next we'll connect pin 4, which is GPIO pin 2, to one side of the black switch. We'll connect Pico pin 20, which is GPIO pin 15, to one side of the red switch. We'll connect pin 3, which is a ground, to the other side of the black switch. And pin 36 on the Pico is a 3.3 volt output, and we'll connect that to the other side of the red switch. Note the differences in the wiring between our 2 switches. And this completes our circuit. Now let's go and take a look at a few code samples we can use with it. Now the first Python script that we're going to look at today to control the RGB LED is kind of a take on the blink sketch. Since we have an RGB LED, we can do some fancier blinking. So this is kind of our hello world. Now we start off the Python script by importing 2 libraries, machine and utime, and you're going to see that in pretty well every one of the scripts that we run today. The machine library is an essential library for talking to all of the I/O ports on the Pico, and utime is used any time that we need a time delay or any kind of a time function. Now we'll start by defining the 3 LEDs that we have, the red, the green, and the blue one, and you'll notice how the machine library comes into play over here. Now notice with the pin number over here, we're talking about the GPIO pin and not the physical pin on the Pico, so make certain you understand that difference. You'll also notice that we define all of these as being outputs, again using the machine library. The while true section of our program is very similar to the loop in an Arduino program. Anything inside this section will just continue to run. And what we're doing is basically just turning on and off LEDs. First of all, we start with the red LED and we set its value to 1, and that will illuminate the red section of our RGB LED. We set the green and the blue to 0, and then we go to sleep for 2, and 2 is 2 seconds. So what will happen is that LED will stay on for 2 seconds, and then we'll go into the next sequence, and in this case we're going to do the green one, etc., etc. We go through all the various different combinations. Then over here we do a print, and that print end of loop is going to appear down over here in our shell at the bottom, so that's where any print statements will come out. And then we'll do a last one, which is all the LEDs off, wait for 2, and then it's just going to go over and do it over and over again. So this is our RGB version of the blink. Let's go and load that now to our Pico, and we can do that like this. And as you can see, our LED is going through the color sequences right now, as we would expect it would. And we've also just printed end of loop up here on the shell, and of course it's just going to go to the beginning of that loop again and just repeat itself. So here you go, the RGB version of the blink sketch running on the Raspberry Pi Pico. Now when you look at the code to test our switches, I want you to keep in mind how the switches were wired. They were not wired identically. Specifically, the red button had one side connected to 3.3 volts, so turning it on would send the signal high, whereas the black button was wired in the opposite fashion. It had one side connected to ground, so switching it on would send the signal low, and neither of them had pull-up or pull-down resistors. Well, we're going to take care of all of that in code. Now, we start off again by importing both the machine and the UTime libraries, and then we define our red button as being the one defined to GPIO pin number 15. Again, that's a GPIO number, not a physical pin, and it is an input, so we define it as an input, and we also define a pull-down resistor on this. Now remember, the red button has one side connected to 3.3 volts, so we want to hold it low all the time, and when the switch is on, it will activate it and pull it high. So we have a pull down resistor over here activated through code. And we do the same thing with the black one, except we're going to be using a pull up resistor in the case of the black switch because it's wired in the opposite fashion. And that is on GPIO pin number 2. And then it's a very simple matter of just doing a test to see if the button has been pressed. So we use an if statement, and we say if the red button value has been set to 1, which will happen when you press it and connect the 3.3 volts to the GPIO input, we're going to print red, and so that's going to print down the shell over here. Now if the black button is set to 0, because remember, it's always going to be set and pulled high by its internal pull-up, but if it goes low because the button has been pressed, then we're going to print black down over here in the shell, and then we put a very slight delay of 1/4 of a second, and that's just sort of a crude attempt at doing some debouncing. And so let's load that up to the Pico. And it's loaded, and let's go and press the red button. And you can see we get red written when I press it. Now I'll press the black button, and as you would expect in the shell, it is printing out black. So you'll notice that we are defining one with a pull up and one with a pull down, and we're defining one as being active when it is a 1 and the other one as being active when it is a 0. So 2 different ways of accomplishing the same thing and getting the input from a push button switch on the Pico. Now in our next script, we're going to make use of a push button and a couple of our LEDs, and we're going to demonstrate a couple of other concepts, one of them a fairly important concept and the other one a useful one. Now we're going to start off by importing the same libraries we have before, the machine library for the GPIO and the UTime for the time functions, and then we're going to define our 2 LEDs just as basically as being outputs, just as we did before, and we're going to set the value of both the LEDs to 0. So the red and the green LED are what we're dealing with, and we're going to initialize them both as being off. And then we're going to go and set up the red push button, and we're doing that the way we did before. Now you remember the red one is the one that is wired to the high side on the other side, to the 3.3 volts. So we have a pull down on the input, so normally that input is low unless the button is pushed. Now what we're going to be demonstrating with this button is the use of interrupts, and interrupts are a very important concept for any microcontroller. Now an interrupt is pretty well exactly what it says. The program is going along operating, and suddenly an event occurs and it interrupts the program, and the program has to go off and service that interrupt before it can get back to doing what it was before. And so we've got that set up down here, and I'll actually move down to this line first to explain it. Now you recall we've already defined button red up over here as being an input with a pull down resistor. Well, now that gives it another property, and that's IRQ, or interrupt request. And we ask it what kind of an interrupt is going to trigger it, and we're triggering it on a rising signal, in other words going from low to high, and that makes perfect sense because this is a push button which will go high whenever the button is pressed. And we have to tell it what we're going to do when we're going to get that interrupt, and that means we need to pass it to a function called an interrupt handler. So we say the handler equals this, int handler, and int handler is indeed the name of the function we've defined over here to handle our interrupt. Now, the first thing we do in int handler is we turn off the interrupts to this pin, so that if another one occurs while we're doing this, we aren't interrupted by our own interrupt, so to speak. Then we're going to print interrupt detected, so that's going to print down the shell over here. We're going to turn the red LED on at that point. We'll keep the green one off, and then we're going to go to sleep for 4 seconds. Now, it's not very customary to go to sleep in the middle of an interrupt handler, but we're just doing this as a demonstration. And then after we finish sleeping, we're going to turn our red LED off. And then we're going to set the handler back so that it's working again. And so this is our interrupt handler that's going to be called every time we get an interrupt generated here by pressing the button. Now, if we go into the true loop, we're going to see what our program is going to be doing when it isn't being interrupted. And it shows another function, the toggle function. The toggle function takes the state of an output and reverses it. So if the output is high, it reverses it to low. If it's a 1, it reverses it to 0, etc., etc. So the LED is going to be either off or on, and we're going to toggle it to the opposite state. Then we're going to sleep for 2 seconds and do it again. So basically we've got a 2-second blink sketch going on here with 2 lines of code. So let's go and load that up right now to our Pico. And you can see that we are starting our flashing LED. And this is what this is going to be doing until I interrupt it, which I can do by pressing the red push button. And I pressed it, and now we've got the red signal, and that's going to stay there for 4 seconds. And then the green's going to start over and over again. And I can interrupt that at any point. I can interrupt it right now. And it finishes there. I can interrupt it when the green one is on. And it finishes there. And if you look up in our shell, you can see that every time I've pressed the interrupt button, I'll press it again, we get an interrupt detected there. And so a very basic demonstration of 2 very important concepts with the Raspberry Pi Pico. Now, this script is essentially an amalgamation of the last 2 Python scripts we looked at, and all we're going to be doing is controlling the RGB LED with the black push button. So we'll start off again by importing both the machine and the UTime libraries, and then we'll define our red, green, and blue LEDs as we did before as being outputs. Then we'll set the value of those LEDs to 0 so that the LED is off, and we'll define our black push button with the internal pull-up resistor. Then we'll go into the true loop, and in the true loop we see an if statement, and we're checking to see the value of the black push button, and we want to see if it goes to 0, because that means someone has pressed a button. If that's the case, we just sequence through the colors. We put the red one on, and we sleep for a second, then we put the green one on, sleep for a second, we'll put the blue one on, and then after that we'll turn all the LEDs off and go to the top again and wait for someone to press the button again. So it's very simple. We'll send that up to our Pico right now. And there we go, and it's the black button, and I'm going to press it. And there we're going through our color sequence. Press it again, and it happens again. So we've essentially combined the last 2 scripts that we've looked at in order to control the RGB LED with the push buttons through the Pico, using both inputs and outputs. Now let's move on to the analog inputs. Like most modern microcontrollers, the Raspberry Pi Pico also has analog to digital converters. So let's work with the analog inputs on the Raspberry Pi Pico. The Pico has 3 internal analog to digital converters. These are 12-bit ADCs, so they have higher resolution than the 10-bit ADC that the Arduino AVR family has. The Pico also has an analog reference and an analog ground pin to be used with an external voltage reference for improved performance from the analog to digital converters. The simplest component that we can use to demonstrate the A to D converters is a potentiometer, and I used a 10K linear pot. We begin by connecting one of the Pico's many grounds, I used the one on pin 23, to one end of the potentiometer. Pin 31, which is GPIO 26 and also analog to digital converter 0, is connected to the wiper of the pot. And pin 36, which is a 3.3 volt output, is connected to the other end of the pot. And this simple wiring completes our circuit. Now let's go and see how we can code for the analog to digital converter. Now here's the script that we're going to be using to demonstrate our analog input, and as you can see, it's another very simple script. We start off by importing the same two libraries that we've used earlier, the machine library for dealing with the GPIO inputs, and the uTime library for dealing with time functions. We then define a variable called potentiometer, and we define it as being our analog input. So we use the machine function, and we're using the ADC function of it to point to GPIO pin number 26, which is also analog to digital converter 0. Now this will only work on a pin that has an analog to digital converter, and on the Pico there are 3 such pins. Then we go into our true loop, and I want you to notice this print statement here. We're basically printing the value of the potentiometer, which should print the value of the output of the analog to digital converter. But notice what we're doing over here. We're using a read unsigned 16-bit output. Now you'll recall that the analog to digital converter on the Pico is a 12-bit ADC as opposed to something like a 10-bit ADC that an Arduino Uno would have. And so with the Uno we would get values back from 0 to 1023 because our 10 bits would allow for 1024 different values. Now with a 12-bit converter, something like you would find on an ESP32 or Arduino Xiao, you would expect values from 0 to 4095 because you can get 4096. But remember, we're going to get this back as an unsigned 16-bit integer. So unsigned being the fact the value is always going to be positive, and 16 bits means it's actually going to be from 0 to 65,535. So the value coming back may not be what you expected, but you will see that this does have its advantages, because when we need to pass this to other operations, such as when we use PWM, as long as we keep everything as unsigned 16-bit numbers, we don't need to worry about things like map commands. Then after we print this, we're just going to go to sleep for 2 seconds and we're going to do it again. So basically we should just see down in the shell the values that's coming back from the potentiometer. And so let's load that up. And we're getting a value back right now. And let's turn the pot all the way to one extreme. And 65,535, that is the maximum value you'll get. So that's when I'm putting 3.3 volts into the analog to digital converter. Now let's go down to the other end. Now on the other end, I've tried a number of potentiometers and I cannot get my value down to 0. Now there is a ground pin on the Pico called an analog ground, and I thought that may have something to do with it, but I've tried different connections exclusively using that ground and having that ground tied to my normal ground as I do right now, and it doesn't seem to be affecting it. It may be my potentiometers or the fact that it's such a sensitive A to D converter, but again I'm going to bring it up right now, and you'll notice these values can go up to 65,535. And so otherwise, that's a pretty simple demonstration of the analog input on the Raspberry Pi Pico. Now in this script, we're going to read the value from the potentiometer and use it as a control for a PWM signal that we're going to feed to the red segment of the RGB LED. So we'll start off by importing the machine and the uTime libraries again, and then we define our LED, and note how we define it differently than we did before. We define it as a PWM output, and then we define where it is, which is GPIO pin number 10. So it's not just an output anymore, it's a PWM output. And the potentiometer is defined the same way we did earlier. And we now have another property that LED red can inherit because it's using PWM, and that's the frequency that it operates at. We're going to set that for a kilohertz. Now we go into true, and there's only one statement in here. We're going to set the duty cycle, and that's the duty cycle as an unsigned 16-bit integer, to the value that the potentiometer takes from the read of the unsigned 16 16-bit integer. So it matches perfectly. We're just going to read the pot and use that as the control for the duty cycle. And that's a pretty simple way of controlling PWM, far less lines of code than you would need, for example, in an Arduino to do the same thing. So let's load that up to our Pico. And let's take a look at the red LED. And as you can see, I can bring it down to next to nothing, although it's still slightly there. And I can gradually increase the brightness of it. And so a very simple light dimmer with just a couple of lines of Python code. Now, one very common component that you're going to use in your projects is some form of display. And so with that in mind, I've attached a small OLED display to my Raspberry Pi Pico. Let's go and see what it takes to get that working. The OLED display we're using is an I2C device, and we're going to run it on the Pico's internal I2C bus number 0. The Pico has 2 internal I2C buses, and there are several options for connecting them up. As this is a display device, we only need to be able to write to it. We are not getting any data back from it. Now for our OLED display, we're going to be using a standard type 1306 OLED display. This is a very common item available in different configurations. Any one of them will work in this experiment as long as the display is rated for 3.3 volts. We'll begin by connecting a Pico ground on pin 33 to the OLED ground. We'll connect the 3.3 volt output on pin 36 to the VCC of the OLED display. Pin 27, which is also GPIO 21, is connected to the SCL input on the OLED display. Pin 26, which is GPIO 20, is connected to the SDA input on the display. And this completes our connections. Now here's the script that we're going to be using to drive our display, and in order to use this script we're going to need to add another library. So go up into Tools and go into Manage Packages, and in the search type in SSD1306. You'll get back a number of results, and one of them will be this module that I've already installed, the SSD1306 module. This is just a general purpose library for working with the SSD1306 type OLED display, which are very common displays. Once you've installed that, you can close it and we can go back to the script. Now in the script we import the machine and the uTime library like we have in our previous scripts, and then we set up a couple of pins, one labeled SDA and one labeled SCL, and we use the machine library and define them to GPIO pins 20 and 21 respectively. Then we set up an I2C object using the machine I2C property, and we pass it the parameters of the I2C object we want to set up. And we need to pass it 4 parameters. The first one is which I2C bus are we using, bus 0 or 1. We're going to be using 0. Then we pass it the pins we're going to be using for SDA and SCL, and we've already defined that over here. And then we pass it the frequency that we want to run the I2C bus at, because this will run at multiple frequencies. Now we use the SSD1306 library that we had installed earlier. We import that and we define our OLED. Now note we didn't have to give it the OLED I2C address because the SSD1306 is a fixed address and that's already built into the library. It does, however, come by different parameters of display, so we have got it to a 128 by 32, and it's using I2C because this library can also use SPI, so we can get a different model of it and connect it a different way. After that, we just start printing out to the OLED with the OLED text, and we set the text up first. So we're going to the Welcome to the Pi Pico display demo. We're going to display that on the first 3 lines. It's a very tiny OLED, and we'll have some very tiny text. And then the OLED shows what it is that we've put into the buffer over here. We're going to let that sit there for 4 seconds. Then we're going to fill the display. We're going to show that for about 2 seconds, and then we're going to empty the display. A fill of 0 does an emptying of the display. We'll show that, And then while it's true, we're going to use the text hello world, and we're going to scroll it. Now the OLED scroll function only moves everything over 1 pixel at a time, so we need to do a number of repeat OLED scrolls and shows, and we do that in this for loop over here with a very slight delay so that you'll see this hello world scroll across our display. And so let's load that up to our Pico and let's watch the display and see what it looks like. And then we're filling, and there's our scroll. And so there you go, driving an LCD display with the Raspberry Pi Pico. Now, being able to control a motor is a very popular application for a microcontroller, and so I decided to hook up a small DC motor with an H-bridge controller to the Raspberry Pi Pico. Let's go and see what it takes to get that working. We're going to be controlling the speed of our DC motor using pulse width modulation from a GPIO pin on the Pico. We'll be using an H-bridge driver that uses a MOSFET for improved performance. For this experiment, you'll be needing a DC motor. I used one that is rated at 6 volts. You'll also need a TB6612FNG H-bridge motor driver. This is a dual H-bridge, but we're only going to be using one side of it. And you'll need a 6-volt power supply for your motor. We'll begin by connecting pin 9 of the Pico, which is GPIO pin 6, to the PWM A input on the TB6612. We'll connect pin 10 of the Pico, which is GPIO pin 7, to the AI2 input, and pin 11 of the Pico, GPIO 8, is connected to the AI1 input. Pin 36 of the Pico is the 3.3 volt out, and it will be connected to the VCC connection on the H-bridge module. We'll also connect 3.3 volts to the standby input on the module. And the ground on pin 3 of the Pico will be connected to the ground input on the module. Next, we'll connect one connection of our motor to the A01 output on the motor driver. The other motor connection is connected to A02. We'll connect the positive side of our 6-volt DC power supply to the VM input on the motor driver. And we'll also make certain that the negative output of our 6-volt power supply is connected to our ground. And this completes our wiring. Now here's the script that we're going to be using so that the Pico can control both the speed and the direction of our motor using pulse width modulation. So we're going to start off by importing the same two libraries we always use, the machine and UTime library, and then we'll set up the potentiometer as we did before as an analog to digital input. And now we're going to set the pins up on the H-bridge controller. That's what these three are here. Now the H-bridge controller has 3 pins in order to control the motor. AI1 and AI2 are used to control the direction the motor spins, and these are set up just as outputs. And then we have a PWM pin as well, and this controls the motor speed, and so we set that as a PWM output on the Pico. So notice the difference between this and this. And then the buttons are set up as they were before, the red and the black button with their respective pull down and pull up resistors. And the LEDs are set up as well. Now they're just set up as outputs because we're not going to be controlling their brightness this time. And then we set the LEDs up so the red and green are off and the blue one is on. So the blue LED will come on at the beginning of this script. We'll set the PWM frequency of our PWM input, and I chose 50 Hertz, but that was just an arbitrary guess, and you can experiment that to see if it affects the performance of your motor. I also going to set the initial value for AI1 and AI2 so that we have the motor spinning in a specific direction. Then we go into the true loop, and we can see in the true loop that we're using the exact same code we used when we were driving the LED. We basically take the duty cycle of our PWM and match it to the value we're reading from the potentiometer. And then we look at the value of the two buttons. Now, if the red one has been pressed, then we set the values of AI1 and AI2 like this, so the motor will spin in one direction. We set the LED red to be on and the other two to be off. If the black button is pressed, we set AI1 and AI2 to the opposite direction, and then we turn on the green LED and turn off the other two. And then we have a small sleep period over here just to debounce the push buttons. And so basically we should be able to control the speed of the motor with the pot and the direction with the two buttons. So let's load that up to our Pico now. And we note the LED is blue at the moment. And we can control the motor. Now let's hit the red button. And the LED turned red and the motor is spinning the opposite direction. We'll hit the black button. The LED is green and that also reversed the motor. And so we can control the speed with the pot. Get it really fast or get it to go really quite slow. And we can control the direction with the switches over here. All with the help of our Pico. Now, the last demonstration with the motor used almost every component on the solderless breadboard. The exception was we didn't use a display. So let's not have our display feeling left out. Let's add the display, we'll write some code that ties it all together, and we'll run our everything experiment. And so here's the code for our everything demonstration, and it's very similar to the code that we used for the motor demonstration. I just added a few OLED functions to it. So we start off again by importing the two libraries we always use, the machine and the UTime library. We define our potentiometer connection, and we define the connections we're making to the H-bridge controller. We define our two push buttons, and we define our three LEDs. We'll also set up an SDA and an SCL connection and define an I2C connection over here, and this will be for our display. We'll import the library for the display and define the display that we're using over here. Now we'll start off everything by printing on the display. So we print the lines Pico motor test onto the top of the display and we show it. We wait for 2 seconds and then we go into the LEDs and we turn the red one on and we wait for 2 seconds and then we turn the green one on and we wait for another 2 seconds. After that we turn on the blue one and we leave it on and we set the motor frequency and we also set these two values so the motor has a direction to go in. And then we go into the true loop, which again looks very similar to the one we use controlling the motor. One difference is this first variable I'm calculating called speed value. It's an integer. I'm determining it by the potentiometer position divided by 500. I came up with 500 experimentally. It's going to be used to create a bar graph on the OLED. And this is the same line you saw before where we control the duty cycle of the PWM wave that's going to the motor controller using the potentiometer. Then when the buttons are pressed, we can illuminate the correct LED and reverse the motor's direction every time we press a button. And then we get down to this display, which is the part that's a bit different. We're going to use the fill rect to make a rectangle on the OLED display. These parameters tell me the position that it starts off in. And this gives me the size of the rectangle. Now speed value is going to be used to determine the length, and that way our rectangle will look like a bar graph. The one on the end here means I want this displayed. We do an OLED show, and then we do the same command again with a 0 on the end so that we can update this next time. Then after that we put it to sleep for 1/4 of a second and do everything over again. So essentially we'll get the same motor demo, but this time we should have a bar graph working on our display. So let's load that up to the Pico. And it says Pico motor test. The LEDs are cycling through their color. And there we go with the fan. And I can do this to change the speed, and you can see it on the bar graph. Reverse the direction if I wish. And so this basically demonstrates that we can combine all of these components together with the Pico and control them all in our everything experiment. And so now that I've got our everything code working over here, perhaps I want to keep this experiment and run it. Now, of course, at the moment it's being powered by the Raspberry Pi, but that's just supplying 5 volts of power because the code is obviously on my microcontroller. So all I should be able to do right now is disconnect it and connect it to a power supply and have it run, right? And we'll do that. It doesn't appear to be doing anything. And when you think about it, of course it isn't doing anything because it doesn't know what to do. The Pico has started up because I've applied power to it, but I've got a number of programs I've placed on this Pico. It has no idea which one of them it would like me to run on boot up. Now there is a way that I can tell it to run this program when it boots up, which of course is going to be essential so that I can take the Pico away from the computer I programmed it on and bring it out into the open, so to speak, bring it out into the wild. So let me connect it back up to the computer and I will show you exactly how we do this. Now first of all, I've disconnected it, so I'm going to have to go and reconnect, and you can see it comes up down here, Raspberry Pi Pico, so I'm connected again, and here is my everything program. And what I need to do to make this program run when the Pico is booted up is I need to save it under a different name. So I'm going to do save as. I'm going to say I'm going to save on the Pico, and I'm going to save it on a special name, and that's main.py. And so we'll call that main.py now. Can send it back up to my Pico so that it's running. And there it goes, we're going, we've got our bar graph. Okay, now let's disconnect this from the Raspberry Pi. Raspberry Pi 4, that is. And connect it up over here. And it's starting off again now. And it's running all by itself without the Pi 4, just on its own power. And so when you want a program to be the default one, you just change its name to main.py. And if I had another program I wanted to change, I would just overwrite main.py with the new program. And so that brings us to the conclusion of our look at the Raspberry Pi Pico, and it is certainly not the last time you're going to be seeing the Pico here in the workshop. For one thing, while I was filming this video, my first order from Pi Moroni of a bunch of Pico-specific accessories has just arrived, and I've made another order from them for some more accessories. I've got another Pico order coming from some other company over here with just a bunch more Picos, so I'm pretty well invested in the Pico, and you'll be seeing a lot more of it here in the DroneBot workshop. Now the best way to find out about these new Pico videos, of course, is to be a subscriber. So if you aren't subscribed to the YouTube channel, please honor me by doing that. Just click on the subscribe button, and when you do, also click the little bell notification, and as long as you've got notifications enabled on your YouTube account, you will get notified every time that I make a new video. Now if you need some more information about the Pico, or if you'd like the code that I used today, you'll find that all in the article that accompanies this video on the DroneBot Workshop website, and you'll find a link to that right below the video. You will also find a link to a discussion thread on the DroneBot Workshop forum that is exclusively for this video. So if you want to talk about the video, discuss the code, or just discuss the Pico in general, the forum is a great place to do that. And finally, there's one other thing, of course, is the newsletter. The newsletter is my way of keeping in touch with you to let you know what's going on here in the workshop, both with the Pico and with all of the other interesting things that we work on. So the newsletter is free. There's information below the video as well for signing up for that newsletter. And it's not a sales letter, it's just my way of keeping in touch with you. And so with that said, I hope you enjoyed this video. I hope it's opened your eyes to some of the things you can do with the Pico. Please stay safe and take care of yourself, and I'll see you again very soon here in the DroneBot Workshop. Goodbye for now.